Hello everyone. Let's take a look at our next problem. There is a set of numbers whose sum is equal to the sum of the elements squared. What's bigger, the sum of the cubes or the sum of the fourth powers? Let me see if I understand this. There is a set of numbers whose sum is equal to the sum of the elements squared. Okay, so for that to be possible, the numbers can't all be non-zero integers unless they're all equal to 1. Because, let's say, just as an example, take three numbers. Take the numbers 1, 2, and 3. They add up to 6, but 1 squared plus 2 squared plus 3 squared is a lot bigger than 6. And if any of those numbers happen to be negative, the sum gets smaller, but the sum of the squares stays the same. So what am I thinking here? The sort of key realization, I suppose, is that if you have numbers raised to if a number is raised to a power and the power is greater than 1, then the result is smaller if the original number is between 0 and 1, right? Okay, so if 0 is less than x is less than 1, then 0 is less than x to the p is less than 1 for, actually, we have 0 is less than x to the p is less than x is less than 1 if p is greater than 1, right? And we also have, if x is greater than 1, then x to the p is greater than x, greater than 1, for p greater than 1. And all of the powers involved in this question are 1, 2, 3, or 4. So, okay, let's just write out exactly what the first statement is saying. It's saying if we add I going from 1 to n of xi, this is equal to the sum as I goes from 1 to n of xi squared. And then we have to compare the sum as I goes from 1 to n of xi cubed with the sum xi to the 4. So is the inequality this way or this way is what the question's asking. I'm almost like, my instinct here at this point is to see if there's a way of formulating this in terms of Jensen's inequality. Based on where I'm finding this particular question, the source for this question, this is cheating, I suppose. I'm cheating. I'm using expectations of what the person being asked this question, what their expected level of knowledge is. Jensen's inequality, I'm sure, is overkill for this, but with some manipulation of what I have written here, it should apply. What is my intuition telling me about which one is true? Well, you know what we can do? Let's just try this for a particular example where we have two numbers. Okay, so let's say x1 is 0.5 and x2 we don't know, but we know that x1 plus x2 is equal to x1 squared plus x2 squared. So what have we got here? Let's solve. We want to solve for x2 now to make this true. So I'm thinking of this as like it's a quadratic equation or a quadratic expression with respect to x2. So for this to be well defined, we have some restrictions on x1. Well, sorry, no, we're assuming we know x1, right? x1 is 0.5, but in fact, if we didn't have this and we wanted to write x2 in terms of x1, this would put restrictions on it because we don't want this, the sign under the radical here to be negative. And so, you know, we could impose that this is positive and then solve for the range of possible values of x1. But in our case, when x1 is equal to a half, now can both of these work? Let's just check whether these could both possibly work. I suppose they can, right? x1 plus x2 is equal to a half plus a half plus square root of 2 over 2, which is equal to 1 plus square root of 2 over 2. Or, if I use the other value for x2, we get 1 minus root 2 over 2. Now let's compute the sum of the squares. 1 over 4 plus, it's going to be a little bit messy, but that's okay. Aha, yes, I have a mistake here, right? This should be a 4. I was wondering why what I was doing here was breaking down so early in my solution, but anyway, okay, 1 over 4 plus 1 over 4 plus 1 over 2 plus root 2 over 2, which is 1 plus root 2 over 2. That's good, right? We expect to get the same thing here. That's how we solved for x2 in terms of x1. And now if I use the other value of x2, I have x1 squared plus x2 squared is 1 over 4 plus 1 minus root 2 over 2 squared. Right, okay, so regardless of how we choose x2, regardless of which of these two things we choose, the condition that the numbers added together is equal to the numbers squared added together, so that holds. Now we just need to check x1 cubed plus x2 cubed. I'll do it for both cases, why not? 1 over 8 plus so that's the sum of the cubes when we take the positive sign. Let's do the sum of the fourth powers. Okay, now let's compare. Yeah, both of these have gotten bigger, right? So what I mean here is, you know, the 9 over 8 is bigger than 1, and 5 over 4 is bigger than 5 over 8. So the fourth power combination is bigger than the third power. I expect the same thing to happen when we use the negative square root, and I'm also starting to see a little bit the intuition behind why this is happening, at least for two numbers. If I imagine a number line, and I have two numbers that satisfy this property, okay? So I've got x1 and x2. I think when I have two numbers like this, if I say that x1 is the smaller number, the one that's between 0 and 1, and x2 is the number that's greater than 1, I believe that this distance has to be greater than this distance. because when I square this number, it's going to move farther away from 1. But in some sense, and when I square this number, it's going to get greater than 1. But if I have two numbers that are equally spaced from 1, then the distance that this one moves is greater than the distance this one moves. Okay, so let's think of this, okay? Let's call x 1. x1 is 1 minus lambda, and x2 is equal to 1 plus lambda. Then x1 squared is equal to 1 minus 2 lambda plus lambda squared. And x2 squared is equal to 1 plus 2 lambda plus lambda squared. So let's think about the distance that each of these numbers has kind of moved in going through this operation here. x1 minus x1 squared is, and x2 squared minus x2 is equal to 1 plus 2 lambda plus lambda squared minus 1 minus lambda, which is equal to lambda squared, well, it doesn't matter how, whatever, lambda plus lambda squared. Okay, so what I'm saying here is if I have two numbers equidistant, two numbers equidistant from the number 1, so something like here and here. When I square this number, it's going to move some distance, and the distance it moves is going to be bigger than the distance this number moves. And so if the two numbers are equidistant from the number 1, then that property of the sum of the numbers equaling the sum of the squares of the numbers cannot hold, because you know this one has lost some value, but this one has gained more value than what the other one lost, and so the sum cannot be preserved. So when I then compare the third power to the fourth power, the sums, the total amount of distance that we're losing from these numbers is going to be dominated by the distance that is gained by these numbers. So my conjecture here is that the fourth powers will be bigger. How do we show this? So this is almost it. If I define the function f, which is just raising all these numbers to the same power and adding up, then at least I know when the exponent is equal to 3, if I increase it a little bit, this sum goes up. But that doesn't necessarily explain well, hold on a minute. Do all the numbers have to be positive? The sum certainly has to be positive, so at least one of the xi's has to be positive. But do they all have to be positive for the original property for this property to hold, do they all have to be positive? Because if they all have to be positive, then these are all positive, then this is greater than 0. Then how can these even be equal? Oh my God, I'm terrible. I am terrible. I am terrible. This is so bad. This is terrible. I am falling into the trap. Oh man, that's embarrassing. I can't wait to put this video online. Can't wait to put this video up. I took the derivative wrong. All right, so this really doesn't help us. I'm not really sure where to take things from here. So the idea I had was to basically look at all these numbers in terms of their relative position with respect to 1, because everything is kind of centered around this number 1. And then the original condition we're given on these numbers gives us a similar condition on the values of lambda. And then when I just try and compare the sum of the cubes to the sum of the fourth powers, I end up, when I take a difference of those things, I end up with this expression in terms of this collection of lambdas. So if this is positive, then the conjecture I've made is correct. I'm very confident that the conjecture I've made is correct. I'm very confident that the fourth powers will be greater than, the sum of the fourth powers will be greater than the sum of the third powers because of the argument I had up here. When you take these things, when you take the numbers to higher and higher powers, the ones that are smaller than 1 get smaller, but the ones that are bigger than 1 get bigger faster than these ones get smaller. I'm just not sure. I'm not sure exactly what what algebraic manipulations I could do here to show that this is true. I'm going to have a think about this one, and I might come back to it with a follow-up. if I can't come up with any meaningful ideas, then I mean, I'll say thanks for watching for now, in case I don't come back to this with anything substantial. But if I have a follow-up in the next short while, then I'll be sure to add it here. So I'm returning to this question after having gotten stuck on it a long time ago. I had one more idea that I thought I'd try to explore. Don't really know if it's going to work out, but maybe as I start working through this, I'll have an insight or some intuition will kick in or something like that. So what I want to do here is think about things a little bit more geometrically. So what I'm going to do is consider a specific case of the problem when there's only two numbers. So along this axis we'll have x1, and on this axis we'll have x2. And we're given in the question that the sum of the two numbers is equal to the sum of the squares of these two numbers. I'm going to say that this is equal to k. And so if I look at just this, then this gives me, the collection of x1 and x2 that satisfy this gives me a circle, and the collection of x1 and x2 that satisfy this equality gives me a straight line. And of course, depending on the value of k, the circle and straight line will intersect in different places. I'm also going to restrict myself for the moment to looking at only positive values of x1 and x2, just to see what happens here. Now, if k is equal to 1, then if k is equal to 1, then the straight line that we have, which is determined by the fact that x1 plus x2 is equal to 1, and this it looks like this, and the circle we have is going to look something like this. It's a terrible circle, but you get the idea. And so we see that either x1 must be 0 and x2 is 1, or the other way around. And in this case, the sum of the cubes and the sum of the fourth powers will be the same. They'll both be equal to 1 because we either have this point or we have this point. So it doesn't really help to think of k equal to 1. So let's think about some other values of k. So if k is greater than 1, what have we got? Well, let's just call this value here now k, and this will be k. And so we have a straight line connecting those. That's the set of x1 and x2 where the sum is equal to k. But now the circle that we have is not going to have a radius of k, it's going to have a radius square root k. Now if k is greater than 1, the square root of k is less than 1. Let's just put it here. Sorry, I didn't. That's not what I meant. If k is greater than 1, then the square root of k is less than k, but it is still greater than 1. That's what I meant to say. So we have the square root of k down here, and the circle is going to intersect this line twice, something like that. Okay, at these 2 points. So the first thing that I'm thinking, eventually when I want to try and extend this to higher dimensions, the intersection, it's not going to be a line in a circle, it's going to be a hyperplane and the surface of some kind of higher dimensional sphere. And these are going to intersect in a higher dimensional generalization of a circle. Now, what can I say if this is the point, the x1, x2 point, what can I say about the sum of the cubes versus the sum of the fourth powers? One way to think about this maybe is to think about the level sets of, if I have xi cubed and call this equal to c, and the sum of xi4 and call this equal to d, what do the level sets of this thing look like? as the exponent here increases, the level sets of sums like this become more box-like, right? As this exponent gets really large, then the level set of, if I have the sum of xi to the p is equal to lambda, as p gets very large, the level set of this looks something like, it starts to look more like a box. Like I think maybe we could. It's not really going to be a proper argument, but like, if I draw, what I want to do is I want to draw the level set of this thing for the value of c, so that it passes through this point, and then look for the intersection of this thing on the two axes, and I guess it'll be slightly below, like for the cube, it'll be a little bit below here, where I have, this is going to be the cube root of k. But then on the fourth power, geez, I don't know. I don't see this working. Or at least not easily and convincingly. Okay, I'm back with this question one more time. I've been thinking about this one a lot for the first time I started recording for this question was almost a month ago. But I've dug a little bit deeper into things, and in fact, I've figured out that the question isn't quite worded properly. And the way I'm going to show that is by giving a counterexample to show that neither of the two sums can be confirmed to be greater than or less than the other one. So let's consider the following three numbers. Now, if I give two numbers like this, and if I have three numbers in total, then there will be two choices for x3, which ensures that the numbers add up to the same as the square of the numbers. Okay, so if I think of this equation as having x1 and x2 being fixed, then this is a quadratic equation for the variable x3. So there are going to be two values of x3 which make this equation hold. They are approximately 1.15 or negative 0.15. So what I'm going to do now is for this set of three numbers, or for this set of three numbers, I'm just going to compute the sum of the cubes and the sum of the fourth powers. In the case of the choice on the left, the sum of the cubes is approximately 3, and the sum of the fourth powers is approximately 3.1. Whereas if I choose this negative value for x3, then the sum of the cubes is approximately 1.47, and the sum of the fourth powers is approximately 1.34. So we can see in one case the cubes add up to something smaller than the fourth powers, but in the other case the cubes add up to something greater than the fourth powers. However, I've also figured out that if we restrict all of the numbers to being positive, then we can conclude that the fourth powers will always add up to something larger than the third powers. So we're going to start with the assumption that the sum of xi is equal to the sum of xi squared as given in the question, but we're also going to force all of the xi's to be non-negative. Now this first equation, I'm going to rewrite this as the sum of xi squared minus xi is equal to 0. And then what I want to do is I want to look at each individual term in this sum and think about what it could be equal to depending on the value of xi. So let's take out one term in this sum, like this. And first, I want to think about the sign of this number, depending on the value of xi. And that's going to depend on whether xi is greater than 1 or less than 1. This kind of corresponds to some of the intuition I had much earlier when I was working on this problem a long time ago, where I just figured that a lot of the dependence on whether xi was greater than or less than 1 was going to be an important part of this question. It turns out that that is one of the key parts in figuring this out. Okay, so let's think about if xi is greater than or equal to 1, then xi squared minus xi will be non-negative. Okay, and this is because if I have a number greater than 1 and I square it, then it gets bigger. So I have a number and I'm subtracting something smaller. So this must be positive. Okay, and this implies xi squared times xi squared minus xi is greater than or equal to xi squared minus xi. And why is that? Okay, well, this number is positive and this number is greater than 1, so it's gotten bigger when I multiply these to get two things together. Okay, now let's think about what happens if xi is less than or equal to 1. This means that xi squared minus xi is less than or equal to 0. So for a similar argument, when I have a number less than 1, when I square it, it gets smaller. And so I have a number and I'm subtracting something which is bigger, I get something which is negative. But what does this mean about when I multiply it by xi squared? Okay, well, I have something which is negative and I'm multiplying it by something which is positive but less than 1. So this means in magnitude, this product is smaller than the original number, but they're both negative, which means that in fact it's greater. You can also think about this as, having a negative number and multiplying it by something which is less than 1 means it'll still be negative, but it's moving closer to the origin. And so in fact, we have this inequality. Okay, so this means if I take every single individual term in this sum and multiply each of them by xi squared, every individual term gets bigger. If each individual term has become bigger, then the entire sum gets bigger. But if I just expand this, this is just saying that xi to the 4 is greater than or equal to, or the sum of xi to the 4 is greater than or equal to the sum of xi to the 3. So in the end, this really boiled down to something very simple. I took a lot of random detours in working out the solution, but sticking with it over the course of about a month, just thinking about it in the back of my mind for a long time, finally ended up getting it. Thanks for watching.